Gravity is not a force. What's gravity? This question might seem easy to answer, but is it? Is gravity just a force, or is it something more than that? When they speak of gravity, humans on Earth typically think of it as a force between two or more masses. I don't know about you, but I always relate gravity to an unpleasant scene: me stepping on a scale. When we step on a scale, the number on the scale represents the pull of the Earth's gravity on our mass. This is what gives you weight. In my case, that's a big number. So is gravity just the pull of our planet, giving us a number on a scale? Keep watching the video to get to know more about it. You'll find out gravity is so much more than just a force. So yes, we know that the gravitational pull is what gives us the sensation of weight. We also know that if we were on the moon, this pull would be weaker and we would be having some trouble going around, just like these astronauts from Apollo 17. So gravity is not the same in all places in the universe, and it depends on the mass of an object. This is a nice starting point. Then, as I'm sure you know, we say gravity is what holds the planets in their orbits. The sun's strong gravitational field is acting on them. Gravity gives harmony to our solar system, at least from what we can see now. What we know is that gravity acts crazy if more than two bodies are involved. In that case, the chaotic evolution of orbits over long timescales takes place. When that happens, some planets can be ejected out of the stellar system, becoming free-floating planets, wandering forever in the dark. But stars are not the only huge sources of gravity. Think, for example, of the gravitational pull of a black hole. As you can see, forces are easy to understand as pushes and pulls. Today we know that, yes, gravity might be seen as a force, but that is only part of a more complex phenomenon. Everything is very well described in the theory of general relativity, developed by Albert Einstein in the 20th century. Einstein was such a genius. It took him a huge leap and critical thinking to detach from common ideas about science as it was seen during his times. Without a radical departure from the idea of gravity as a force in particular, we wouldn't have the theory of general relativity. Of course, general relativity is an exquisite theory, and it works from a mathematical point of view. But people were quite skeptical about it when it first came out, because, as Carl Sagan once said, extraordinary claims require extraordinary evidence. But soon they found this evidence. I would say Einstein's theory is a very extraordinary claim, but it has also had extraordinary evidence over time. For instance, out there are several extraordinary experiments that confirm the curvature of space and time. This is predicted by general relativity. It is perhaps the most important result of the whole theory. It's basically the key to accessing the gate of a new world. Einstein started thinking about his theory when he noticed that everything in a gravitational field falls at the same rate. Stand on the moon and drop a hammer and a feather, and they will hit the surface at the same time. The same is true for any object regardless of its mass or physical makeup, and this is known as the equivalence principle. Since everything falls in the same way regardless of its mass, it means that without some external point of reference, a free-floating observer far from gravitational sources and a free-falling observer in the gravitational field of a massive body each have the same experience. For example, astronauts in the space station look as if they are floating without gravity. Actually, the gravitational pull of the Earth on the space station is nearly as strong as it is on the surface. The difference is that the space station and everything in it is falling. The space station is in orbit, which means it is literally falling around the Earth. This equivalence between floating and falling is one of the most important assumptions Einstein used to develop his theory. According to Einstein, gravity is not a force between masses. I mean, Newtonian physics is still valid, and therefore gravity is also a force, but it's much more than that. In a more general way, it is an effect of the warping of space and time in the presence of mass. Let's keep it simple. We can make an example. According to basic physics, an object will move in a straight line if no force is acting upon it. For instance, imagine drawing a line on a sheet of paper. If you then twist or bend the paper, the line will no longer appear straight, even if your hand is still going straight. In the same way, the straight path of an object is bent when space and time are bent. Take a moment and think about it. If it sounds hard to you, it's just because it's counterintuitive. Among other things, this also explains why all objects fall at the same rate. Naively, gravity warps space-time in a particular way, so the straight paths of all objects are bent in the same way near the Earth. A hammer and a feather will fall together. Thank you for the easy explanation, Einstein. So what kind of experiment could possibly prove that gravity is warped in space-time? How do we know this is really the case? According to Einstein, light bends when it comes closer to a mass. Moreover, since the path is bent, it deviates from a straight line, and therefore the crossing time is greater. Basically, it will take you longer to follow a curve from point A to point B than a straight line from point A to point B. In the case of light, this effect is known as the Shapiro time delay. Erwin Ira Shapiro, born October 10, 1929 in New York City, is an American astrophysicist and Timken University professor at Harvard University. He has been a professor at Harvard since 1982. Now the thing is, the deflection of light was a well-known phenomenon, at least theoretically. I mean, Newton's theory itself predicted the deflection of light, but the difference is that general relativity predicts it will be deflected twice as much. Now, it is often argued that since light has no mass, it shouldn't be deflected by the gravitational force of a body. This isn't quite correct, because light has energy, and according to Einstein, energy is somehow equivalent to mass, via the famous formula E equals mc squared. The effect was first observed by Arthur Eddington in 1919. Before telling you the story, though, I want you to think about it. How would you test the predictions for the deflection of light? Which conditions do you need to have in order to observe it? Remember, we need a beam of radiation coming towards us and a mass distorting the space-time between us and the source of light. I'll give you a moment to think about it. In the meantime, why don't you subscribe and press the notification bell? So what did you think about it? The secret is, for example, to watch the light of stars during a solar eclipse. This is what Eddington did in 1919. He traveled to the island of Principe off the coast of West Africa to photograph a total eclipse. He had taken photos of the same region of the sky sometime earlier. By comparing the eclipse photos and the earlier photos of the same sky, Eddington was able to show the apparent position of stars shifted when the sun was near. But most importantly, the amount of deflection showed that Einstein's computation was right, not Newton's. That was amazing. A beautiful confirmation of the theory of general relativity. Nowadays, we know that light from distant quasars and galaxies gets deflected when a cluster or another galaxy, or perhaps a clump of dark matter, gets between us, the observers, and light source. This famous phenomenon is the so-called gravitational lensing, and it has been used to measure the masses of galaxies, and even see the effects of dark matter. As one might think, the deflection of light makes it travel along a slightly curved path that is a bit longer. This means light from a planet on the other side of the solar system from Earth reaches us a tiny bit later than we would otherwise expect. The first measurement of this time delay was in the late 1960s by Shapiro. In order to show this, radio signals bounced off Venus from Earth when the two planets were almost on opposite sides of the Sun. The measured delay of the signal's round trip was about 200 microseconds, just as predicted by general relativity. As you can see, it is much more than just a force. But these are not the only effects of gravity. Let me introduce you to gravitational waves. We said stars basically warp the space around them. Now let me ask you, what do you think happens around a binary star? These are systems of stars made of two components. They both warp space-time, creating ripples in space-time, similar to the way swirling your finger in water creates ripples on the surface. Moreover, due to loss of energy, the two stars gradually move closer together, an effect known as inspiraling. They basically fall on each other and eventually they merge. As they get closer and closer, they move faster and faster, and their orbital period becomes shorter. So in order to get close, they must lose energy. But how do they lose energy? General relativity predicts this will happen as a consequence of gravitational wave release. And indeed, this is what scientists Hulse and Taylor noticed when they were studying a rapidly rotating neutron star. These stars happen to radiate radio pulses in our direction. The pulse rate of pulsars is typically very, very regular, but the two astronomers noticed that this particular pulsar's rate would speed up slightly, then slow down slightly at a regular rate. They showed that this variation was due to the motion of the pulsar as it orbited a star. As they observed their pulsar over the years, they noticed its orbital period was slightly getting shorter. They were witnessing a general relativity phenomena. The pulsar was and is spiraling due to the radiation of gravity waves, just as predicted by Einstein's theory. Amazing, isn't it? But this isn't the end. Gravity is responsible for a bunch of other phenomena. For example, there is the so-called frame dragging. Because the Earth is rotating on its own spin axis, it not only curves space-time by its mass, but it also twists space-time around it. This twisting of space-time is known as frame dragging. We know this because we've seen it. How? Well, the frame dragging has a consequence of the fact that if you put a gyroscope in orbit around the Earth, you will see its axis of rotation changing in a very precise fashion. If there is no frame dragging, then the orientation of the gyroscope shouldn't change. If there is frame dragging, then the spiral twist of space and time will cause the gyroscope to precess, and its orientation will slowly change over time. Well, guess what? We've actually done this experiment with a satellite known as Gravity Probe B. The experiment, launched in 2004, used 4 ultra-precise gyroscopes to measure the hypothesized warping of space and time around a gravitational body, and frame dragging, the amount of a spinning object pulls space and time with it as it rotates. GPB determined both effects with unprecedented precision by pointing at a single star, IM Pegasi, while in a polar orbit around Earth. Good job, NASA. So do you still think gravity is just a force? That's all for this video. Thanks for watching. I hope you enjoyed it. See you next time on the channel.